I'm not.
Okay, so that is the formula for finding the total impedance of a parallel RC circuit. And the phase angle between voltage and current, let's go back to my little vector diagram. I have that angle there, and the tangent of theta is equal to IR divide opposite over the adjacent, IR divided by IC. But, and I could, if I had my currents, I could use that as it is. But what I'm going to do is find the tangent of, I'm going to find theta in terms of R and XC. So IR is VS over R. And IC is VS over XC. The numerators cancel, I do my little algebra flip, and the XC ends up on top, and I have XC over R. Is that right? That just doesn't seem right. I think it's the reverse of that, but I'm not getting that in my derivation. Oh, I know what I did. Real simple, I flipped these. This resistance is the reference current. It should be that. The reference is always your resistor since there's no phase shift. So I flip those two vectors. And this should be that. Okay? I'm still not seeing it in the text, but that's what it is. So theta is equal to the tangent the arctangent of R over XC. It's just the opposite of this guy right here. See that? Series is XC over R, parallel is R over XC. So there's that equation, there's this equation, and that's parallel. So these guys are quite a bit different, aren't they? It's not as straightforward as you might think. Okay, let's do a multi-sim thing for parallel RC circuits. Then I want to show you a filter, an RC filter, and that will pretty much wrap up chapter 10. Guys ready? Or not? You ready? What'd you get? What'd you get for the total current?
Oh, was it okay? I was like, this doesn't look right. For XM3,
Yep.
I got 6.668.
Okay, hang on. So you got milliamps?
Oh, I closed my thing, I don't remember.
That's the voltage.
Oh, I was looking at the voltage.
I got a 185.186.
185.186. Okay. How about the current through the capacitor?
112.560.
Okay, and how about the one through the resistor?
147.056.
Right, so do they, when you do the vector algebra, does it add up?
Does the heartbeat?
Yeah.
Yeah. Well, mine was off by like.
A little bit?
Yeah.
And what about-
185, 191.
What about for a phase angle?
I had 37.43.
Okay, everybody getting that? It's just a matter of plugging in the numbers. So, the only difference between the parallel and the series is that we're using the current as our vector offset, if you will, if you want to put it that way. Okay? Does anybody have any questions? Okay. Now, in the book, I want to mention something about this term in the book called power factor. Keep that. We've been looking at circuits, whether it's parallel or series, and noticing that overall the current and the voltage are not in phase. Something less than 90 degrees. And so when we've been studying resistor circuits, the voltage and the current have always been in phase. And so in order to calculate power, we've just been multiplying voltage times current, or V squared over the resistance, or the current time squared times the resistance, and then call it a day. That's it. The two waveforms, whether it's direct current or alternating current, they're in phase, voltage and current, so the equations are relatively straightforward. But when you have a capacitor, and we'll see this also in inductors. When you have an RC circuit like that, where you have voltage here, and current is offset by some angle, could be anything. When voltage is at a peak, the current is not necessarily at a peak. And so you can't really use these equations. Even if you're using RMS values, you can't really use those equations to determine the amount of power that is being consumed or produced by the source. The equation, in fact, has to be adjusted by what is known as power factor. So the equation for the total power delivered to a load in an RC circuit is it's similar to this guy here, but there's a little bit of an offset. It's power is equal to voltage times current times the cosine of theta, where theta is the difference between the voltage and the current. Theta is this guy here that we calculate. All right, and this term here, cosine theta, is called the power factor. And it is there because in a capacitor, when the waveform, when an alternating current, when the voltage is increasing in one direction, the capacitor is charging. And when that waveform begins to drop and head back down towards zero, the capacitor is now discharging. In effect, the capacitor is turned into a little battery for a portion of the waveform, and it begins to discharge. So the capacitor, ideally, it consumes power from the source, delivers power back to the source. Consumes power, delivers power. And that phenomenon has to be accounted for in our power equations, and it's accounted for in that way with the cosine of theta. All right, that's called power factor. If you think that, if you just imagine your home, in your own home, if you think that power is delivered from the utility to your home, and that's it, that's not an accurate description of how things work. Maybe for your home, for the most part, that's true. Power goes from the utility to your home. But if you worked in a huge industrial facility where there's all kinds of motors as part of a process, you've got energy being stored in those motors in the form of electric fields, more so in the form of a magnetic field, because the motors operate on the principle of the interaction between two magnetic fields. But the same principle applies. When that AC wave is going from the maximum value down towards zero, the electric fields in the capacitors, let's say you have battery chargers and you have a lot of fork trucks with battery chargers there. Battery chargers typically have a lot of capacitors inside. Those electric fields are delivering power back to the utility for a portion of the AC cycle. And if you have a lot of those, if you have a lot of battery chargers, let's say you're a distribution warehouse, Amazon or whatever, Walmart, massive facilities that are 1 million square feet, over 1 million square feet in area. You've got fork trucks all over the place. The utility that is delivering power to a facility like that, for a portion of every cycle of the AC wave, you have power being delivered back to the utility. So you have this back and forth. And the utility has to overcome that. They have to build a power generating facility large enough to overcome the power being delivered back to them by these capacitors. If it gets too much of an effort to do that, utilities will bill customers based on poor power factor. And they will begin utilities will begin to surcharge customers based on poor power factor, which means that the customer has so much heavy equipment that the utility has to overcome that all the more to deliver power to the load. And there are companies out there that provide power factor correction equipment, so that as far as the utility is concerned, they're not really seeing a lot of this backfeed. It's actually being handled internally within the facility itself. And that's one way to overcome it. It's a huge business in and of itself, power factor correction. But whenever you hear that term, that's what it's all about. And actually, it's not so much a result of capacitors as it is motors in a big industrial environment. Motors are huge violators of, huge consumers of energy in terms of magnetic fields, and they're expanding and collapsing, and when they collapse, they deliver power back to the utility, and that's not a good thing. So that's what we call power factor. It's the cosine of the angle between voltage and current, okay? That's in the book. I wanted to touch on that just a little bit. The other thing that I wanted to show you was, so you probably should write that formula down, power factor. That's usually referred to by the lowercase letters PF. PF equals cosine theta. The other thing that I wanted to show you is how a circuit responds to, how an RC circuit responds to frequency. If you have a circuit like this, you connect that to an AC source. And if we have if we're taking, we connect the resistor on that circuit to an output. We want to feed something else downstream of that resistor. An interesting thing happens when you have an RC circuit. It has to do with the capacitive reactance of that capacitor as a function of frequency. Let's say this is an AC source that is capable of producing output power at different frequencies. So it's what we call a function generator. You have one on your desk. It's this guy right here. So if you fire that guy up, you can select square wave, triangle wave, AC wave, and you can change the frequency. If you're measuring the voltage, for example, here with a meter, you will note that for a fixed capacitor, as I increase the frequency of my function generator, of my AC source, as I increase the frequency, what happens to the capacitive reactance?
It decreases, right?
It decreases. So whenever I increase the frequency, the capacitive reactance in ohms of this guy goes down, and the voltage across that goes down, and therefore the voltage across this guy goes up. In proportion, much more of the voltage is dropped across that resistor. Increase the frequency a little bit more, this continues to go down, and a little bit more of that voltage is dropped across the resistor. And that process continues. And so what happens is that if I were to take and graph the voltage drop across that resistor as a function of frequency, I would see something like this. And at some point it would begin to level off. So this is known, this kind of a circuit is known as a high-pass filter. High-pass filter. and you will see this in communication equipment, transceivers, transmitters, receivers, quite a bit. It's a simple RC circuit. And the output of this might be feeding an amplifier or some other circuit downstream. And so if I want to amplify high frequency signals, and if I want to minimize the amount of amplification that I get from low frequency signals, I will use a simple RC circuit, pull the output off the resistor, and that will do what I'm looking for. So low frequency signals will get cut out, high frequency signals will get passed to the next stage of whatever equipment it is I'm feeding. That's called a high pass filter. By the same token, let's just say I flip these guys. I have an RC circuit, and now I'm pulling my output off the capacitor and not the resistor. What's going to happen there? Just the opposite. As I increase the frequency, this is going to go down. The voltage across here is going to go down. At low frequencies, a lot of that voltage from the source is going to get dropped across the capacitor, and I have just created what is known as a low pass filter. And the curve, the output curve, is going to look something like this. Just the opposite. So that's DC. Okay? So I will be, if I wanted to amplify lower frequencies and pass the low frequency signals onto another circuit, I pull my output off the capacitor. If I want to do the opposite and send higher frequencies to another circuit, I pull my output off the resistor. Do you want to do a little multi-sim? Take about 10 minutes. Okay, we're going to do one more and then call it a night. This is just build a simple low-pass filter circuit on multi-sim, and just do the frequencies on the front of that page from 0.1 kilohertz to 12.5 kilohertz.
Okay.
The function generator on that multi-sim is, I think it's the second instrument down on the right-hand side. Right below the multimeter. Yeah, right below the multimeter. And while you're working on that, let me have your other labs. Do you have your other ones? Did I give you 3 already?
Yeah.
This is the 4th one.
Yeah.
Wow. I'm working you. These? Yours? All righty. Jared? Okay, good. We got a lot of grading to do this week. Is this yours? It's yours, okay. A very rough
Just a rough
sketch,
draft?
very rough sketch, yeah.
Oh, that's why I'm
That's pretty good. Give us a detail. That's pretty good. It's really good, great. Characters, how they races.
Let's give it a reason more.
You don't have to stop, you don't have to. You don't have to. It shows it's on the front. I just, oh yeah, okay. Speed runner. You can't read, so what do you do? You don't do it. Nope. No, you're missing.
Oh, you're,
You probably don't know.
No, that's fine, yeah, this is too.
And you can,
Change that from the one hundred, get out.
yeah, I was just gonna say, you don't have to turn the circuit off to change this code. You can just change the, actually, you're gonna be changing the code. Yeah, but you have it, do you have it set for covert? Yeah, so all you do is just change the frequency, and then this will automatically change.
Okay.
Yeah.
Thank you.
That looks good. Yeah, we're starting point now. Yeah, run it, click on the meter and see what the readings are. It's gonna be, you're gonna be
These
but
things
it
are
would be alternate. So go ahead and click on it and see what you get.
How much?
Hang on a second.
Thanks.
You should stick that fence to shut them here.
Oh, yeah, yeah.
No. So I don't want to break my temple.
Oh, that's first right there. Just the level up there.
I need a touch. I should change the, I should change the light, please. I should change the wall to the ground, please.
That's what I get. 14.
So it is.
So now you can change this without doing anything, that meter will automatically
I mean, if they
update.
don't want it, so I just.
Yep, just on the front page.
I have 20 contracts.
You all done?
Yeah, it was just like a reference.
Very rough, very rough. Did you get it?
This is probably just a regular board. You got what I do.
Don't forget your homework for next week, guys. In case you didn't get it. I'll be posting it anyway. Thank you.
See you next week.
Yep, see you.